We proved the ex, polynomial approximation as far as single independent variable is concerned. So we proved it by integration by part. Now the time has come that we will provide the proof for the multivariable polynomial approximation of a function, a proof that is not available anywhere. Okay, a proof that is being provided through us, because I have personally seen so many proof available in many books and at many places, and people are just kind of meandering. This is what I felt. So solution is something that should be as easy as possible. So that is called solution. Solution never means that your solution is very good, because it is too complex. The best solution is always very easy. So that is called the best solution. So we will provide you the solution that is very easy. Now first we see that what is polynomial approximation as far as multivariable is concerned. Okay, so that is the idea, that what is the polynomial approximation of any function that is multivariable. If I have a function fxy, function f is has two independent component x comma y, two independent components. Now, if I have a function in as a polynomial order of one, we can say it monomial. So if I have a function as monomial, then function can be x plus y. Function can be x plus y. If it is x plus y, then if I have function fxy, z equal to fxy, where this is xy plane, this is xy plane. If this is xy plane, then this is x-axis and this is y-axis. This is y-axis, this is x-axis, then this is fxy. Function over xy points toward the vertical. If that is true, then this is z. Z equal to fxy. If this is z, then this is x and this is y. This is fxy, function over x comma y. Now, I have a kind of, if this function exists, then fxy equal to x plus y. If that is the case, then how I can reproduce fxy as another function gxy? That is the question. Now, to reproduce it, gx needs dz by dx and dz by dy. Two partial derivative it needs. What is partial derivative? If I have x and y axis, and then I have a surface, 3D surface, then if I make a cut along xz axis, I make a cut along yz axis. If I make a cut along xz axis, then it is 2D, not 3D, where this is x-axis and this is z-axis. And then whatever surface we had, now surface is a line. If that is the case, then what is dz by dx? In 2D, when we derive the integration by part, the f that gx equal to fx0 plus f dash x0 into x plus f double dash x0 into x square by factorial 2 and so on. There we had this as x-axis and this as y-axis or fx. So now here, if this is x-axis, then this is fxy, where it is only cut we have made along xz plane. Now that is z. So if there was a surface, now in xz plane the surface tends to align a curve dz by dx. Similarly in yz plane, if this is y and this is z, then what is dz by dy? Partial derivative along x-axis and partial derivative along y-axis. The partial derivative along x-axis is dz by dx, partial derivative along y-axis is dz by dy, where this is fxy or dz or delta z. So that is the scenario. Now, if I have fxy, if I have fxy, now if I have fxy equal to x plus 1, okay, if I have fxy equal to x plus 1, that is the kind of fxy. If fxy is x plus 1, then what is dfxy by dx? That is 1. Dfxy dy, then it is 1. Now, gx, when we are writing a polynomial approximation of fx, this is what we call. But right now, we are trying to replicate fxy as gxy, where fxy equal to x plus 1. If that is the case, then dx needs two partial derivatives. The partial derivative is said as 1 and 1. Now, if that is the case, partial derivative is 1 and 1, and if I want to replicate x plus y, then it will be dz by dx into x plus dz by dy into y. Now, they are same. So, the first order, if gx is polynomial of first degree that is mirror of fx, then dx is nothing but f dz by dx into x plus dz by dy into y. Okay, so I can create an exact replica of fx as gx when we get dz by dx and dz by dy from fx, and I write dz by dx into x plus dz by dy into y. Dz by dx and dz by dy are 1. Then now you can change x plus y to alpha x plus beta y, and if you do the differentiation, it will become alpha and beta. Reproduce here alpha x plus beta y. Same. Now fx is in power of 2, x plus y whole square. Then x square plus y square plus 2xy. Now, if I want to reproduce fxy exactly as gxy, then gxy would say that if you have the fxy equation is only in power of 2, that is x plus y whole square, that is x square plus 2xy plus y square. Now, gxy is said to replicate fxy as it is. If that is the case, then gxy is saying, can you give me two dual order, double order partial derivative? That is, it wants fxx means d2x by dx square, fyy d2x, d2y by d2z by dx square, that is fxx, d2z by dy square, that is fyy, and d by dy of dz by dx, that is fxy. Now, dz by d2z by dx or d2 fxy by dx is 2x. X square is 2. First it becomes 2x, then it becomes 2. 2 d2z by dy square is again 2, y square changed to 2, and dx and fxy, d of dy, d by dy of dz by dx, d first we calculate dz by dx and then whatever comes dz by dy, then 2xy will become 2, otherwise other thing will become 0. If I calculate d2z by dx square, only x square will convert to 2, other will become 0. Now I have three partial derivative and then I am giving it to gx. Now gx, when it want to reproduce x square plus 2xy plus y square, what it would do now? It would say x square into d2z by dx square divided by 2 plus then it will, okay, now it has to replicate 2xy, okay, then it would 2xy that it wants to replicate. If that is the case, then it would say that fxy means d by dy of dz by dx means fxy into x into y. If fxy is 2, then 2xy plus y there it is y square, here it has to get y square, then it is y square into fyy divided by 2. Then exact replica of fx as gx as far as dual order is concerned, then it is df, it is fxx by 2, or I would say factorial of 2. Why factorial of 2? Because when in fx it was x square, I do first derivative and it became 2x. Actually it is 2x to the power 1. If I do derivative again, then it becomes 2 into 1 x to the power 0. So it is factorial 2. Now if I say gx, then gx is nothing but d2z by dx square into x square divided by factorial of 2 plus d by dy of dz by dx, that is fxy, into xy plus d2z by dy square into y square by factorial of 2. If I do this, then it becomes x square plus 2xy plus y square. It is exact replica of the fx. Now, if I go for third degree, that is x plus y to the power 3, then it becomes x to the power 3, y to the power 3, 3x square y plus 3xy square. If that is the case, if I want to replicate that fxy as gxy, then gxy would say I need triple partial derivative. Then it comes as fxx fyy. 2xy means fxxy and fxyy. If I do fxxx, then only x to the power 3 will remain, other will become 0. If I do fyy, then y to the power 3 will remain, other will become 0. If I do fxxy, then only 3x square by y into y will remain, other will become 0. If I do fxyy means d2z by dy square d2 by dy square of dz by dx. First you calculate dz by dx, whatever comes, then do 2 times derivative on it with respect to y. So fxyy. If I do fxyy, then term that is 3xy square will remain, other will become 0. Now I have 4 triple order partial derivative. Now I am giving it to gxy. So first one is fxxx, then it is nothing but factorial of 3, because x to the power 3, first derivative is 3, then into 2, then into 1, that is factorial of 3. So if someone want to replicate fxy as x plus y to the power 3 x cube plus y cube plus 3x square plus 3x square y plus 3y square x or 3xy square, exact replica of in gx through partial derivative, then he would try x to the power 3 multiplied by d3z by dx cube divided by factorial of 3, then it will be equivalent. Similarly, plus fyy or d3z by dy cube into y to the power 3 divided by factorial of 3 plus then fxxy means d by dy of d2z by dx square fxxy into x square into y divided by factorial of 2 plus fxyy into x into y square divided by factorial of uh, okay, so factorial of 3, because if it is 3x square y, then if I do first time derivative, it becomes 3 into 2xy. If I do again derivative, it becomes 3 into 2 into 1y. Okay, then if I do again a derivative with respect to y, then it becomes 3 into 2 into 1 into 1. So it is actually factorial of 3 into factorial of 1. What? Now the exact replica of fxy as gxy is d3z by dx cube into x cube divided by factorial of 3 plus d3z by dy cube into y cube divided by factorial of 3 plus plus d by dy of d2z by dx square into x square into y factorial of by factorial of 3 by factorial of 3, not 2, factorial of 2 by factorial of 2 plus d plus dy d2 by dy square of the dz by dx into x into y square by factorial of 2. Y factorial of 2 is we had 3x square y. Now I want to get back as 3x square y. Now 3x square y became 3 into 2 into 1. So I'll take 3 into 2 into 1 means it is 6. Now if I replicate it here with the d by dy of d2z by dx square, then that is 6. If I divide by factorial of 2, then it becomes 3. That side also d2y by dy square d2 by dy square of dz by dx, that is fxyy, that is also 6. If I divide by factorial of 2, then it becomes 3. This is what we want. So what we want is x cube plus y cube plus 3x square y plus 3y is 3xy square. X cube plus y cube plus 3x square y plus 3xy square. To get that, I have now fxxx into x cube divided by factorial of 3 plus fyy into y cube divided by factorial of 3 plus fxxy into x square into y divided by factorial of 2 plus fxyy into xy square divided by factorial of 2. It becomes exactly as fx, that is x plus y to the power 3. Now we can go along x plus y to the power 4. This is one thing. Or we can go more in the independent variable as fxyz, that is x plus y plus z, x plus y plus z to the power q. And now we have x plus y to the power q. Now we can have x plus y plus z to the power of q. In that case, if it is x square into y into z, then I have to do dual differentiation along x-axis, then y-axis, then z-axis. Then whatever scalar we are getting, that scalar I have to fit in the dxy and divide by a number that is appropriate to get back the same coefficient. So now this is the formulation that we have got, that fxy can be mirrored in gxy. Now if fxy is set of all the polynomial to the power 1, 2, 3, 4, then gx we make set of all the polynomial. Now gx, when we say that full-fledged the polynomial approximation of gx, when there are two independent components x comma y. So if fxy, then gxy, x comma y, two independent variable, exact approximation of fxy, full polynomial. If you want the equation, it is fx into x plus fy into y plus fxx into x square by factorial 2 plus fxy into xy plus fyy into y square by factorial of 2 plus fxxx into x to the power 3 by factorial of 3 plus fxxy into x square by into y by factorial of 2 plus fxyy into xy square by factorial of 2 plus fyy into y to the power 3 by factorial of 3 plus so on. Now, if I take fx as black box in the sense fx may be set of all the polynomial and sin x, exponential, logarithmic, this is what I used to say. If fx is everything and some of the polynomial is also missing, x to the power 1, then y x to the power 3, something like this. If fx is a black box and then I want to get a gx as polynomial approximation of fx, then gx would say that what is your maximum degree. Then fx would say my maximum degree is n. Then please give me fx, fxx, fyy, I mean all the partial derivatives possible. Then using those partial derivatives, it would set it in the big polynomial form with the degree of 1, 2, 3, 4, 5, 6, 7, 8, and so on. And then we get the gx, that is polynomial approximation of fx, where fx is a black box. So that is the idea. Now, concern is, can we prove this formula? We proved through differential equation. We differentiated each degree and accordingly we replicated into gxy and we came to a formula. If it is x to the power 3, then it will be fxxx. If it is y to the power 3, then it is fyyyy. If it is x square y, then it is fxxy. If it is xy square, then it is fxyy. If x square y, then x to the power 2 and y to the power 1. That will lead to factorial of 2. So then I have to divide by factorial of 2. If it is xy square, then power 1 and power of 2. If I multiply, it will become, I have to divide by factorial of 2. So here x to the power 3 means factorial of 3 I have to divide, xy to the power 3. Factorial of 3 I have to divide. So this is the formula that we got in gxy from the fxy as approximation from the differential point of view. What about integral point of view, which is not available anywhere else? Now let's see that I have fx is a function equal to, okay, now if I see the fx equivalent of gx, single variable, not dual variable, single independent variable. If I have fx, then equivalent of fx is gx. Gx is nothing but x into fx. I mean x into f dash x, df by dx. df by dx is f dash x, we can say. F and on top of it single quote and in braces x, that represents single derivative. So df by dx into x. What is the rate of change of fx when there is one unit change? How much fx change? How many unit fx change when there is one unit change along x-axis? That is df by dx. If I know the rate of change df by dx and I multiply it by width, I get the altitude. That is fx. Fx equal to dfx by dx into x. Slope or rate of change into x into df by dx, or f dash x into f dash x equal to fx. Width into rate of change is height. Okay, now let's see that what is fxy. I mean fx equal to, or we started with gx. Okay, so gx equal to x into f dash x. Now let's consider that I have a function fx. Then any function fx, I can represent it as, any function fx, I can represent it as x into f dash x. Now fx, when we were thinking about polynomial approximation in 2D, then gx equal to x into f dash x. Here, if I do the polynomial approximation in two independent variables, fxy and gxy, then gxy equal to, I'm not talking about whatever we have talked prior. Okay, if I have gx and I want in term of kind of the width and rate of change, then it is f dash x into x. If I have f dash x, I can say gx fx whatever. So if I have rate of change and if I multiply by independent variable, that is the width side, then it gives the fx or gx. Now in 2D, in 3D, if I have xy, then rate of change along x-axis, that is fx. dfx means dfx by dfxy by dx, or we also say dz by dx. dfxy by dx, that is fx. fx into x, rate of change along x-axis multiplied by x, gives the height z in the xz plane. Now rate of change along y-axis into the slope, that is dz by dy. dz by dy into y will give height along the z-axis. If I add these two height, then we get the actual height. Okay. So if I want to calculate vertical component, if I want to calculate vertical component at any point x comma y, I have a point called x comma y. I want to calculate the vertical component at x comma y. At x comma y, what is rate of change along x-axis? What is rate of change along x-axis? That rate of change into whatever x I am taking, that x if I do, then I get the height. So 1 unit change if I make, then I get the respective z value. So dz by dx is nothing but per unit change. How much is the per unit change in x? How much is the unit change along z-axis? That is dz by dx. If I have rate of change along x-axis, that is dz by dx, if I multiply by any x, so if rate of change is varying, it's not constant. If it is varying per x, if I move x, the rate of change also varying because dz by dx is a function of x. Then at any x, at any point x, okay, if I multiply dz by dx by some width, then for that width, it would give me the height. And same way, if I go along y-axis at any point y, okay, so if I multiply by full y, then full z it will give at that location. If I go in x and multiply by x dz by dx, for full x I get the z. Here for full y I get the z. Now what is the net z at point x comma y? That is the question. So x comma y, what is dz by dx multiplied by x plus what is dz by dy multiplied by y? If I add these two, I get the net z. This concept has to be clear from all the possible corners, then only we can proceed. If I have fx equal to df by dx into x, if I have two dimension, if I move along x-axis at any point x, what is the y? At any point x, what is dy by dx? That is rate of change. Per unit change along x-axis brings how many unit change along y-axis? So dy by dx, if I have at point x, okay, suppose I take x as 10, then what is dy by dx at 10? If I have that scalar value and if I multiply by full 10, then I get y at that location. Now in 2D plane, I have x-axis and y-axis. If I take any point at x comma y on the xy plane, then what is the z value? First, I'll see the rate of change along x-axis. That rate of change into x, that will give me the vertical calculation as far as x-axis is concerned. Okay. Now, if I go along y-axis, dz by dy into y, what is the vertical? So, if this is the surface, okay, if this is the surface where along x-axis it is going down, whereas along y-axis it is coming up. So, this is the surface. Along x-axis it is going down, along y-axis it is coming up. At any point x comma y, what is the vertical? That is the question. So, at any point x comma y, if I see dz by dx, then it is negative. If dz by dx is negative, if I multiply by x, then the z what I am getting, that is I am getting negative. Whereas along y-axis it is slope is positive. The dz by dy is positive. If dz by dy is positive, then multiplied by y would give me some value. That is the vertical. So vertical that is computed along y-axis, vertical that is computed along x-axis, both are different. One is negative, one is positive. If I add and if it becomes positive, this proves that z at any x comma y is positive. If it comes as negative, then z at any x comma y is negative, even though the dz by dy into y is positive. Okay, so now any function fxy can be represented as gxy as x into f dfxy by dx plus y into dfxy by dy. Means fx into x plus fy is nothing but dz by dy. Fx into x plus fy into y is is any function. So if I say fxy is represented as gxy, then gxy equal to fxy equal to fx into x plus fy into y. Now if I see the single variable, then gx equal to x into f dash x into f dash x. Here gxy equal to x into fx, partial derivative along x-axis, or x, there it is x into dfx by dx. 2D. In 3D, it is x into dfxy by dx plus y dfxy by dy. There x into dfx by dx, x into dfx by dx. Here x into dfxy by dx plus y into dfxy by dy. If that is the case, now we have kind of polynomial function or polynomial expression, polynomial approximation in 2D as x into dfx by dx, and in 3D x into dfxy by dx plus dfxy plus y into dfxy by dy. Okay, so this much is understood. Now, but this is our principle, means how we will proceed. Anyway, this is well known. Now consider that dfx by dx, the slope what we are talking in 2D is 1. If it is 1, then gx equal to x or y equal to x. If slope is 1, means y is changing at same rate as x is changing. So y equal to x. Here in 3D, z equal to x plus y. In 2D, if dfx by dx is 1, then y equal to x. In 3D, if dfxy by dx and dfxy by dy, both partial derivative are 1, then z equal to x plus 1. Then equivalent of a line that is y equal to x, if I take this through 2D to 3D, where this line, I mean this is a line, if this is a line and y equal to x, this line can be have equivalent in 3D, this line becomes surface now. If surface is x plus 1, then it is exact equivalent where both partial derivative is 1. If slope along x-axis and slope along y-axis both are 1, then z equal to x plus 1. If slope along x-axis in 2D is 1, then y equal to x. So y equal to x is same as z equal to xy. One is line and one is surface. So x equivalent of in 3D is x plus y, not x into y or x minus y. So the line equation y equal to x has equivalent in the surface as z equal to x plus y. When dz by dx is 1, dz by dy is 1. 1, 1, now x plus 1. There fx equal to x into df by dx. When df by dx is 1, then fx equal to x, means y equal to x. So y equal to x is same as z equal to x plus y, 2D and 3D. Straight line at 45 degree converted to a surface at 45 degree. Okay, if that is the case, then we have gx equal to x into f dash x, x into df by dx. Now, now the equivalent, if that is true, x into f dash x, then equivalent here is x I will replace with x plus y. This is what we are saying. X is replaced with x plus y. Now f dash x would be replaced by f dash x comma y. Now if I see 2D and 3D, 2D is x into f dash x, that is gx. In 3D, if I replace x with xy, now x is one independent component, here independent component is two, that is x and y. So if I have a function y equal to fx equal to gx equal to whatever, equal to x into f dash x, then if I map into 3D, means two independent components, then gxy equal to, or z equal to, or fxy equal to x will become x plus 1, x plus y. This is what we saw in bracket, x plus y into f dash x comma y. There f dash x is dfx by dx. Here f dash x is dfxy by xy. Now xy is nothing but plane. There dfx by dx means we are differentiating fx with respect to x-axis. Dfx by dx. Here dfxy by x comma y means we are differentiating fxy with respect to xy plane. So x into dfx by dx is equivalent to x plus y into dfxy by x comma y. X plus y is a surface into the differentiation of fxy with respect to the xy surface. X plus y into dfxy by x comma y. If now we will break this. So x plus y braces into f dash x comma y. Now if I break it, then it becomes x into f dash x comma y plus y into f dash x comma y. But the original gx is x into fx plus y into fy, f, and divided by f and bottom x, fx, x into fx plus y into fy. Now fx is nothing but d fxy by dx, and fy is nothing but dfxy by dy. But right now we have is, what we got is x into dfxy by x comma y, f dash x comma y, plus y into dfxy by x comma y. If I see both equations, one is x into fx plus y into fx, and one is x into f dash xxy plus y into f dash dash differentiation x comma y. This proves that when dfxy by x comma y is with x, then that is nothing but dfxy by dx. If dfxy by dx comma y is with y, then that is nothing but dfxy by dy. This proves that f dash x, when it is at x, near x, then it is fx, dfxy by dx. F dash x comma y, when it is with y, then it is fy, that is dfxy by x comma y. Okay, mean dfxy by dy by. Now we have got it. Now if I have polynomial expression in 2D, I can map it to 3D. Now polynomial approximation in 2D is nothing but f dash x into x plus f dash dash x into x square by factorial of 2, f dash 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 x into x to the power factorial of 3, x to the power 3 by factorial of 3, plus f dash 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 4 into x to the power by factorial of 4. Now I have to calculate equivalent here. Now I'll replace x with x plus 1, x plus y. Now it becomes x plus y into f dash x comma y. That result in x into f dash x comma y plus y into f dash x comma y. That is nothing but what we saw is x fx plus y fy. Now next is f double dash x into x square by factorial of 2. Here it becomes x plus, here it becomes f double dash x comma y into x plus y whole square by factorial of 2. Then it becomes x square plus y square plus 2xy into f double dash x comma y by factorial of 2. Then it becomes f double dash double differentiation d2 d2x comma y by dxy square. So f double dash into x square by factorial of 2 plus f double dash xy into x comma y plus f double dash x comma y into y square by factorial of 2. Now when f double dash xy is near x, means it is fx. So fxx x square by factorial of 2. fxy into xy plus fyy into y square by factorial of 2. Now let's go to third term. That is x to the power, that is f triple dash f dash 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 x d3x by dx square f dash 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 x into x to the power 3 divided by factorial of 3. Now if I convert it here, f triple dash x comma y into x plus y to the power 3 factorial by 3, then it becomes f triple dash x comma y into x to the power 3 divided by factorial of 3 plus f triple dash x comma y to the power x square into y by factorial of 3 plus f triple dash x comma y into x into y square by factorial of 3 plus f triple dash x comma y into y to the power 3 by factorial of 3. Let's settle it down. f3 double 3 dash xy means fxxx into x to the power 3 by factorial of 3. f triple dash x comma y into y to the power 3 becomes fyy into y to the power 3 by factorial of 3. Nice. Now if I have f triple dash x comma y into x square into y by factorial of 3, it becomes by factorial of 3, but it is not like that. It is 3 into f triple dash x comma y into 3x square by y by factorial of 3. That is the exact. Plus f triple dash x comma y x into y square into 3 divided by factorial of 3, because 3 is coming there. So now f triple dash x comma y into 3 into x square into y, it will become fxxy into 3 into x square into y by factorial of 3, means by factorial of 2. 3 by factorial of 3 is factorial of 2. So fxxy into x square into y by factorial of 2 plus fxyy into x into y square by factorial of 2. Now you can move ahead with x plus x to the power f 4 times dash means d4 fx by dx4 f dot dash 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 x into x to the power 4 by factorial of 4, that is gx. If I bring it here, then f4 dash x into y bracket x plus y to the power 4 divided by 4 factorial. Now it is the homework that it is exactly not same what it should be. So it will be same and you can continue. So this is the new way of proving the multivariable approximation, multivariable fx, polynomial any function fx polynomial approximation, that is gx, when it is multivariable case. Now we can do same with x plus y plus z or x plus y plus z plus k, whatever. Now same thing, the first is x into f dash x, that will be equivalent to x plus y plus z plus k. Now that it will start. Now the f dash x y z k will be fx, fy, fz and fk. Same way fx, xxx, fyy. Same way it will move. So this is the way we can do the any function fx, the polynomial approximation in gx with gx where multivariable is concerned, where we saw that how we can use whatever we did integration by part to get the gx in the single independent variable to get the same thing in equivalent same thing in gx as far as multiple variable is concerned, where f dash x means the change in fxy with respect to unit change along the surface. Delta a area, there it is delta x, here it is delta x into delta y, delta area. That becomes fx when it is near x, fy if it is near y. This is what we saw and then we moved ahead. So this is homework. So we'll try for the x to the power 4 also, but right now it will take time. X to the power x plus y whole square into, or x plus y to the power 3 into x plus y. Now if I do the computation, then whatever comes, then I have to do as fx, xxx, fy, y, and divide accordingly and see if it comes in factorial form the way it is in f. So this is something that is precious and this is ours. So we are filing disclose. Every video we have a disclosure. So we have around, I believe, more than 250 videos where we have disclosures. So 250 disclosures are pending, that we will see how quickly we can find. So that we will see. So beyond this, in minima maxima calculation, we will see closed region and then bounded region, closed region, one bounded region. What are these? Then we will see conditional maxima and minima. So that those things that you will see. So maxima minima is very big, because with maxima minima multivariable, especially you calculate the kind of the benefit a company when he is producing many items, and the many items and its price in the market, production price in the market, and whatever the expenditure has come doing the production. So this kind of maximization in the benefit profit as far as more than one product is concerned, how it can be achieved. So that is a big thing. Means this is not only calculus multivariable maxima and minima. It could maximize any company's production. If company has expenditure, okay, investment, and then so it has invested in the production, and then it is going to the market to the sell. If I have all the formulation as multivariable, because many products are concerned and many features are there, then we can maximize the production, we can maximize the profit. So this is not that simple what we are seeing. So we will proceed on.